That was, yes, that's correct one. Oops. Mm-hmm. All right. What did we talk about yesterday? Or, I mean, yeah, what are we doing since Friday? So since, yeah, what are we talking about? Hmm? No, but if you can put in the context of the overall topic of the course, yes. About RDL system for the RDF, yes. Mm-hmm. But I mean, so what is the motivation here? Hmm? Make a structure of objects. Yeah. To represent knowledge, So in the first part of the course, we talked about logic. So standard logics, a little bit of fuzzy logic. So the formalism that allows for reasoning. So kind of formally implement reasoning. In the second part of the course, we are talking about some practical aspects on how to represent a knowledge that it is suitable for to interface with logics and build logic-based reasoning. And then it was question of, by the way, what's your name? Adam. Huh? Adam, yes. So Adam asked yesterday. So where and whether these techniques that I'm talking about are used in today's technology. So I posted some links in Canvas. So let me see. So here is our Canvas. I think it's no, it's the wrong course. I need to remove this link. Yes. Modules. So I don't know if you checked the Canvas today before a meeting, but I populated with some links. So some fresh links. What I want to say is that it's not that ontologies is something kind of is a mainstream developer's technique, so to say that. I mean, you can easily point to a company that does development of ontologies. So still, and again, so I'm personally I'm interested in ontological descriptions from a research angle, and in connection to really learning and neural representation of categories. So my understanding that it is still a hot topic. Moreover, so still there is a debate in the research world about the way how to represent knowledge and implement reasoning. So so these debates happen in conferences, international conferences, and different fora. So one of the forums that I found is the Ontology Summit, so which happens I think every year. So there is already a plan for Ontology Summit for next year. And then if you scroll, so what's interesting is that so the topics they discuss is really so the relationship of ontology-based systems with large language models, ChatGPT and such. So to me, I mean, this kind of little information that is present here in this description tells that I mean it is an active research debate. So what technique is better captures cognitive abilities such as reasoning. And so also I see that people are talking about hybrid systems, which I also kind of more in favor, so to say, or I think we will see emergence of hybrid systems. Hybrid in a way that's, I mean, like formally represented knowledge and representations, hierarchical representations learned through big data analysis. So one thing. Second, so if we go back, and then the second thing is I think has practical importance. Industrial ontologies. So there is a need to describe technological domains formally, so to represent knowledge, to implement reasoning. So I mean, this type of reasoning so it's a rule-based reasoning to, for example, to facilitate diagnosis of faults, to facilitate kind of generation of new medicines, even, you know, if you know, if you do with or if you work with genetics and see which kind of genes are more responsive to what and such, diagnosis of diseases, etc. So all these questions are considered within industrial ontologies initiative. So here I found an organization which is a kind of international organization with very outdated certificate, but also with lots of useful information. And so in this context, so ontologies, in a way, how I'm kind of I introduced to you in this course, they are used so for describing domain knowledge. Then maybe one useful thing which I found interesting was also a video. Yeah, I'm presenting a motivation.
Thank you.
So I will not watch it, but I mean it provides with some interesting links where ontologies are used and challenges. So please have a look at these sources, and again, so maybe who knows, maybe in the future you will deal with knowledge representation, and in this case this information will be practically useful. But again, at the same time, so I also have to admit that the idea with semantic web, where it all has started, maybe not most popular nowadays. So it's, yes.
I'm curious, have you ever been to the ontology conference?
Me not. I Let me think. No, I mean, are you kind of, if you continue your line of reasoning? So what because maybe I have some experience from elsewhere. Not on the conferences. Also, I collaborated with the industrial ontology group in Finland. Some long time ago. So that was very active. I mean, the members of this group was very active on these summits, and I also, I mean, as part of this collaboration, I think I reviewed a couple of 2 or 3 PhD theses in this domain. So, and again, so my knowledge about the research state of the art maybe is a little bit outdated. The most recent acquaintance with the ontologies happened within my research area, which is again a special computational technique to bridge the, I mean, you can think of it as a neurosymbolic approach. So to bridge the learning and structured knowledge representation. So they, so I invited a group from France. So there is an active researcher. So, and that's a good news. So this is news as of last year. So there are active research groups working on ontological descriptions using OWL and looking for novel ways for kind of positioning and contribute to the state of the art. I don't know. I mean, very vague answer to your question about my participation in ontological conferences. But again, so I hope this alone is a good enough motivation to look at some more details on how knowledge is represented practically. Okay, so let's go back. Yes. And today I will show you some practical tools on how to work with ontologies, and before also what do we mean by creating ontologies. Yes, to begin with, some definitions, some more research definition or definition taken from a research paper. Ontology is a formal, explicit specification of shared conceptualization. So formal is linked to machine readability. So that's the main motivation. So you want to create such a description, specification that is easily processable by computers. So explicit specification means that we are about to really describe concepts, properties, functions, axioms, etc., etc. And so share it means that we create this description and we agree on this description amongst several parties that will be used for taking decisions. And conceptualization. So it will be, I mean, it can serve as an abstract model of a certain domain. So the simplest analogy when we talk about ontology is just empty questionary form. So a form without any field, without any information filled in. And so here, what you can see some hierarchy. Oh, well, you can see different concepts. Like we have a concept called employer. It has so this concept has one set of attributes. So it could be I mean, on the same, thinking in the same direction. Another category, which is different from an employer, which could be, I don't know, restaurant. Also with similar set of attributes, obviously. And then some other categories which has nothing to do with the employers, but altogether they define or they used to describe maybe a single resource. In this case, it's a person employed somewhere. So this is what we are about to create. And then, so again, ontology is used to introduce a vocabulary. So we need kind of agreed. We need terms on which we agree to reason about something. So autonomy is anatomy is one of the examples with the terms for the organs and the processes and the relationship between them. And terms remain terms or just information without meaning. So we need to describe. So we need to give meaning to this terms. And here is an example. So heart is a muscular organ that is part of circulatory blood circulatory system. So here is I mean, this sentence itself is kind of I mean, it suggests rather sophisticated structure. So we have terms, we have definitions, we have relationship, part of so some kind of partonymy. So and which interconnect different systems, and we have a kind of a global category which contains kind of more stuff. And in logic, in the first part of the course, so we kind of resorted to really the product of formalization. So we assume that we have some variables, functionals, which have this meaning, and we could apply the rules of logic to reason in terms of finding again in terms of deriving a meaning of certain relationship described through logical operations. So ontology elements, concepts with the hierarchy, properties of concepts and properties also may have hierarchies, and so keep this in mind. So properties are a special species. Restrictions applied to properties, and different relations between concepts. And we obviously at the end of the story we have instances that kind of possess the that include all these concepts and properties above. So, and we are about kind of creating a description to make us relevant to this first order semantics. So it means that we have individual resources, and then I mean, we should kind of create them. We have classes that actually I mean, according to certain properties unite different individuals, so according to some common properties, and also we have relationships. So we have properties of resources, and then again in the first order logics semantics. So we may we have this kind of possibility to define intersections or unions of classes and such. So that's what we are about to create. So we in a way we want to create a language or a support, so programmatic support to describe all this complexity. Again, on the level of definition, so we have so when talking about ontologies, we have a terminology component, or we can identify a terminology component and an assertion component. And well, here it's kind of this components introduced as kind of boxes, really kind of linking to graphical representation. So graphical representation is always it comes side by side with some structured language-based representation, obviously. And here is just clarification what it is, what is meant by terminology component of an ontology versus assertion component. So assertion is really the instance. Instance of certain or statement about instances of certain terms. So it's like different levels of abstraction, so to say. In the simplest way, so we need some extra we need some extra syntaxes to what we have learned last time about RDF to describe this richer hierarchy. So we need, and in the simplest case, we can use this extended version of RDF. And remember, RDF is Resource Description Framework, which actually allows us to describe more complex relationships. So this extension is called RDF schema. Yes. So RDF schema, and again, so when talking about ontologies, it's very useful to switch on your object-oriented programming skills. So it's pretty much similar ideas. So you have classes, you have some inheritance, and such. The only thing is that so the main diversion here is that in ontologies we describe properties kind of separately from classes. So properties are classes by themselves, and they can be applicable to other classes. So it's not like in object-oriented programming you have a class and then you have properties that the instances of this class might have. So properties may exist kind of separately from classes, and then they can be applicable to other classes in different combinations. So we start with this simple example. Let me see. Maybe I can give you 5 minutes to talk and maybe even discuss how would you approach it. So yesterday when we talked about describing resources, we used this subject predicate object format. So that was the job of RDF. So now we want to add more information to the picture. So we want to say that Mary Mary is a woman, John is a man. They are both persons, and so Mary has, I mean, that has husband is a property of a woman, actually. I mean, on the high level hierarchy. So let me stop talking for 5 minutes. Do some drawings of this possible hierarchy, and then we see. I mean, how I mean. So my version of it, basically. Yeah. So just try to sketch, you know, categories, categories, properties, and relationship between them. And the purpose is to, I mean, I will not ask you to show your drawing, but maybe you can match later on. So what you have reflected to what you see. And tell me when you're kind of happy with your drawing. So shall we trace it and see? I mean, how much it corresponds. And of course, you know, I mean, there is no kind of ultimate solution. I mean, there is a kind of maybe common ways to define the categories, but at the end, it is basically up to the developer to do this kind of mapping. So, but let's again see one possible way to describe this simple statement. So, and again, remember, yesterday we talked about describing resources. So that's the only thing. So we wanted to transition from information to kind of this more formalized resource description now. And also yesterday we said that the specification of these resources would exist elsewhere. So now we are about to see how this elsewhere can be constructed. So we start with Mary and John, which is actually the assertion part of the ontology, and the property has husband. So oops. So now again, so my input to you was obviously Mary is a female person, and John is a male person. So basically, we have a woman, and again, so here, so we talk about we introduce one kind of generic class for everything, like the starting point. So we have RDF class from which all other classes are kind of branched out. So, but the important thing is we have woman as a class. Then we obviously have a man as also as a class. Then we have an instance, again, an assertion of a property. And a property is a class in itself. So we have different properties which may have also different hierarchies, and we can build the relationship between properties and or instance of a property and the specific class to which we apply. So, and here, look, I mean, the same property can be applied a little bit differently. So, or you can specify that this specific property is applied to a class woman. So so in the terminology of ontologies, so we talk so the domain for the property, the validity domain for the property, is a class woman, and and this property is actually a range. So it defines possible kind of values or possible objects which it span over, and so we just define so that the range for this property is this class man. And so finally, well, there is no sequence in what I mean, kind of the time sequence and aspect in what I'm presenting, but man and woman are both subclasses of a person. That is a class in itself. And on this higher level of hierarchy, so people may have spouses, partners. And partner is a kind of more abstract category. So it's a property. So again, you see, so has spouse is a property, which is more generic than has husband. Is domain is a person, and the range is also a person. So it kind of includes like anything. And in this case, we can, so you see hierarchy of properties, so emerging hierarchy of properties. And all this, so now we are, so this is a graphical representation, and now we want to kind of to describe using some specific syntaxes. And for this, we use RDFS. And you probably can recognize, so this text is written in notation 3, so N3 format. So subject, predicate, object. So again, so very similar. So the only thing, the extension here, so this RDFS component comes from these special quantifiers, which actually to which meaning some extra meaning is loaded. So person is a class. Woman is a class, etc., etc., a subclass of and such. And so the syntax is defined in in these prefixes above. And one of the prefix here is to a specific ontology where I mean all this knowledge will be saved. So we are engineers of this knowledge, and we create a description which we save in a certain file, which we make available publicly. And now I will show you practically. I mean, what does it mean? So first of all, as yesterday, I want to show how to convert it first to RDF or XML format, so serialized version of it, so spelled out, and then how to place it. I mean, how to make it available for sharing. So maybe I shall do this. To do this, and of course, I mean, you can do same. You can try same thing offline on your own. Just by copying. Just remove this thing. So what I want is I want to just copy this whole thing. Control C, and then I want to go to is it this? No. Yes. To the N3 to XML conversion. A different thing. Oops. So output format RDF XML. Here we go. So we take this input now, this out. Control C, and then now again. So I just want to check its validity and possibly visualize. So this, I go to the validation service. So all the links you find in the previous class. So and I want to display triples and like a graph. So yes, here it is. Oh, maybe I can. So what do we see here? Let me see. So this is our hierarchy. We have Mary, and at the end we have class. So I will not spell it out, but I mean this is the automatically generated knowledge model that we have created. And so the message here is that we made it machine parsable. And at the end, so we also have a way to even to visualize it for knowledge engineers. But that's not it. So I mean, so far I did it all manually, so just copying and pasting. So the whole idea with ontologies is that you share it with others. So you create your knowledge base for a specific domain, and you make it available. And others also do that, and so that later on people can connect. So it just link the reasoners to yours and others ontologies to perform semantic searches. So how to do that? So what do we need for that? For this? For this, we need a server, obviously, a publicly available server with a public IP address, and a web server that contains this description as a file. So as simple as that. Before I show this to you, I want to make the kind of leap transition to something which is called OWL. That we actually will be using. So RDFS, so I introduced this RDFS as extension to RDF, to Resource Description Framework, to represent more complex knowledge, or more complex knowledge than just describing resources in subject, predicate, object manner. So the next step is to describe more complex relationships between classes. I have a slide that spells out so what kind of relationships they are. But the next transformation of RDFS is something which is called Web Ontology Language, which is called OWL. And actually, I mean, syntactically, so the difference is minimal. So you just need to point out to the schema where syntax is located, and it has some extra primitives to describe, for example, properties. So you can these are highlighted in red. So if you do this, so you can also visualize in the same manner. So first convert into XML, and then to validate and describe. But what I want to show you is how to make it publicly available again. So first, only wait a second. Yes, what is it? LS. No, it's still on. Good. So this is my web server. I have created it in cloud, Amazon Web Services. How many of you have tried AWS or worked with it previously? Amazon Web Services? 1, 2, good. 2?
Yeah, 2 also.
2 people, 1?
And 1 online.
2 people, 3 sold. Okay, good. But then maybe, I mean, I can give you some interesting hints, because I mean, I personally always have this problem that sometimes you really need to create a server, and create a server with an IP address, and then and not only IP address but also with the DNS name of the first tier, so that kind of publicly available. So I decided to give you again, I will not spend time kind of spelling out all this stuff, I guess. Not? Yes. So I put some. I put a recipe, like a very quick how-to on creating your own server. There are multitude of ways. I mean, there is nothing you have to take it as the only way to do. You may, I mean, maybe I may assume that you have, you know, standalone computer. I mean, working as a server, but already configured with the DNS and a public IP address. Then you are good. But again, for those of you who ever come across a need to create a computer running on public IP address, so Amazon Web Services is very straightforward way to do. So let me see if I have it somewhere. Yes. So first of all, your starting point is no, not that one. RDS.com. So it's Amazon Web Services. You create an account. Yeah, disclaimer that you need to provide a credit card, but it doesn't cost anything. And then, when you complete the procedure, well, actually, I mean, it's a full-blown cloud computing service where you can create incredibly complex distributed computing facilities, easily manageable. But I mean, here I'm just resorting to the fact that you can create a single virtual machine. So it is called instances. So in the terminology of cloud computing in general, so you create an instance, and it's a virtual machine like anything else. So and then when you start, I personally like Linux based. I mean, when it comes to service server functionality. And so basically here you can create like an Ubuntu machine, and you can choose a configuration which is totally free of charge, which is important. And then when you boot it, so you are given a public IP address, and this is a dynamic address. So if you want to have a stable one that exists throughout time, lifetime, so you have to pay for that, but actually it's not needed. So every time you boot or reboot this instance, so you will get a new one. But what you can do, again, so I don't know, maybe you know all this, but again, if you didn't know, then there is a service. There are many of such, but like what I'm using is noip.com. Yes, so it just gives you names, domain names for your public IP addresses. And just for the purpose of this course, I created a name which is called D0034E-23-OWL. So this one over here, so you can try it out. So there is a very beautiful, very beautiful web server, so the default web page of Ubuntu. But then there on the server, I have created a folder where I keep all the ontologies that I create. And what we are about to do, we now will create a new file, which will be called example.owl. And I do it well in the console. So I established SSH connection there. So let me see, where am I? Yeah, so I'm in the ontologies, and I copied the text. So I mean, there are different ways. So you can create locally, you can use SCP to upload, and then, well, you know it. So I use VI, very beautiful text editor, and I call example .owl. So I create a new file. So let's see. Yes. Okay. So something like that. I hope it will work. What? Whatever. Ah, yeah, of course. I cannot do it as a user. I need to do it as a root. E and Control B, escape. So now I have it here locally, example O. So it means that if I go now to my browser, and somehow Safari doesn't work. I mean, doesn't display XML files correctly, but Chrome does. So now if I reload it, so now I have this example OWL file. Ah, you don't tell me. It won't. Now it won't work because let me see, because it's in the inappropriate format. So not all web tools have this automatic conversion from N3 to RDFS. So what I need to do, I need to do this extra step. No, not yet. Where? Ah, sorry. It was here. Yes. So what I want to actually do this, and I want to put this, and I want to convert it to maybe I missed one dot. Yes. Yeah. So this text I will copy now to the file. So I will do it very quickly now. The easiest way. So now, escape. Okay. So let me see. If I now go to here and I reload it, so okay, so it looks like XML format. So what you can do with it, so now this knowledge model is available publicly, and it means that others can easily access it. I mean, just to demonstrate again, so I use this visualization tool. So visualization tool, let me see. Web visualization OWL. The addresses exist in PDF. So this is the new version. So this is the old version. So it's, if by some reasons new doesn't work, so try the other one. But here, what you do, so it's a third-party service. So by default, it displays some ontology. But what I want, let me just remove this stuff. I want to take this address, Control-C, and I put it as a address here, and I have to visualize. So what happens now? So obviously, so this software, this server takes the ontology from my server and reads it, and again be able to automatically process it. So well, it doesn't show the instances, but it shows the class hierarchy. Okay. Next. Again, all this you can try yourself. Not required for the test, but again, if you want to play around with this tool and for your data, then you can do that. Yes.
We're going to use AVS for?
Huh?
What are you going to use?
Well, here I just use it to create a web server, basically. So that's it. But again, so you can. To me, just this is kind of the quickest way to get a server up and running on public IP address, which I can link to DNS.
Do you want to do topologies on the server or?
Yeah, I mean that is it. I mean, so the ontologies, they make sense in the context of. I mean, it's of kind of distributed knowledge knowledge model. So you place your ontological description and make them available somewhere. So on the internet, publicly available. And then you may connect to these different ontologies online and use it for reasoning. Let us have a short leg stretching, a couple of minutes, and then I will continue with something else.
What's your research again?
It's well, topic-wise, it's on the intersection of deep learning and symbolic data representation, knowledge representation.
Okay.
And but technically, I use special kind of computing, which is called computing with randomness, where you can kind of model symbolic operations with some algebra, and then you can use the results of neural networks in these computations for producing kind of knowledge of this type, or vice versa. So if you have, for example, an idea that the phenomena that you want to learn in the in neural networks has certain structure. For example, so you want to learn on graphs. So how to interface it to a neural network. So neural network it has a flat input. So, but you want to kind of encode. You want to represent a structure of your domain, so that you learn on the kind of on this hierarchical data, not on just simple single fields. And so with this technique that I use, we can do that kind of natively. And then it is further on. It is linked to this novel hardware. Like I don't know if I mentioned this neuromorphic hardware.
Yeah.
So I mean, you can then kind of interpret. I mean, the results of this computation as spiking patterns on this novel processor. So I mean, all these computations can be done in spikes, basically. So, which in long term leads to more energy efficient way for implementing machine learning functionality. But it's more or less like, I mean, on a high level, it's more like deep learning plus plus. So, and we try to kind of with this technique, we try to optimize operations even within the learning pipelines, neural networks.
Cool.
Something like that. And I also am kind of also a high level concept. I'm interested in more unsupervised learning.
Okay.
So because how knowledge emerges from just observation, basically.
Like clustering and stuff.
Clustering, self-organizing maps, so neural architectures for unsupervised learning. Yeah.
But you work with ontologies as well?
Actually, not at the moment. How to put it? I mean, it is my wish to kind of look closer into this domain.
Yeah.
I mean, from the standpoints of that theory that I'm working with, but I didn't have, say, a reasonable project for doing that yet. But I mean, my internal project is actually this course, because I mean, when we had this idea that we need a kind of a course on knowledge representation and reasoning, I thought maybe it's a good time to get involved in more in the with ontologies and stuff. So I mean, it was a bit of even some learning even for me last. I mean, 2 years ago when I refreshing. But yeah, I mean, but still, I think it's a challenge. I mean, so there is no kind of good understanding how really artificial intelligence, like artificial general intelligence, should be built, because I mean, where you really can do this kind of complex reasoning, where you can reason on, you know, part whole, you know, relationships, derive new properties like with logic. So that's what happens with ChatGPT. Nobody really actually understands what's going on there. So that's why I think if people have spent so much time on kind of understanding the relationship, I mean, how to just and creating some semantics for some language support for describing this knowledge, I guess it should be somehow reused. So I believe really in the hybrid solutions. So but, that's kind of in my on my wish list to look at. Right. Shall we continue? So now that was a kind of a quick transition. So from RDFS to OWL, and I want to more formally introduce OWL, which is actually the language for describing ontologies, and that's what you will use. You will try in lab 2. And once again, so I want to make it clear, the point with lab 2 is really to learn by trying. So, and here it's not that you need to solve something really complicated problem, but really to understand maybe the mechanics behind knowledge engineering and representation. But back to OWL, it's a actually it is a family of languages for knowledge representation. So we have I developed, well, a long time ago, 10 years ago, first version, and an upgraded version 2009, still a long time ago. But again, so it is a standardized description. So as such, I think its validity is way longer than the probably current popularity or current usage. So you can rely on the tools and compliance of the tools to this standard with this stuff. So the main motivation for OWL was syntactic limitations of RDFS to describe resources in sufficient details. And here in red, I showed what categories couldn't be described by RDFS. For example, yeah, well, again, so probably I don't need to go through each and every one, but for example, representing knowledge, and this here probably I can link to your reading in the first part of the course of these chapters about knowledge representation. So it was quite lengthy reading, you remember, and it was quite some science, so to say, behind how to represent this and that, so these ranges and such. So so the toolbox of methods in logical description is very large, and so RDFS captures only this tiny portion of it. So there was a need to kind of for a more complicated to describe more complicated cases, and so here you see examples of some of this. And I think even yesterday I mentioned that some properties, obviously, they can be applied in combination with properties of other classes. Like, for example, a property can be a transitive. So if a bolt is a or a nut is a part of a wheel, or a tire is a part of a wheel is a part of a car, so tire is part of a car, obviously. So that's transitivity. So same for inverse. So you can have symmetrical property like friend of, or inverse property. So like has supervisor versus is supervisor of, so they are inverse properties. So RDFS didn't have the support. All does. Yeah, but this is the highest high-level hierarchy of class and properties, which is and here are some constructs that are used. No stress. You don't need. You wouldn't need to kind of construct it by heart, but I mean just for your now visual reference. And again, so what I can tell that you probably can easily match to what you I mean to your current knowledge of logic and reasoning, formalism. So. And this very slide demonstrates that all is actually capable of describing quite, yes.
So if you were to summarize, what do you say is the biggest difference between RDF and OWL?
Well, yeah. So the kind of logical sequence here is RDF, RDFS, OWL. RDF is just for describing resources like facts in the standardized way of triple subject, predicate, object. So no semantic is added. So this is just a mechanical way of annotating resources. I mean, relationship between resources. On top of it, you want to build. You want to add semantics, so meaning to categories, and the semantics can be of very complex nature or of different complexities. So you can remain on some rather simple level of kind of class hierarchies and property hierarchies. That's it, and that would be the job of RDFS. If you want to further add complexity on types of properties, so that properties can be transitive and very symmetrical, then you need, so RDFS doesn't have the support simply. So it's like, I mean, you maybe transition from, I mean, it's not correct comparison, but from assembler to C to C++. So I mean, something that you cannot express in C++. At least it's hard, but I mean, it's I mean, depending on where you're sitting, so it's impossible to kind of do this very quickly in assembler or so. So that's the relationship.
Quick question.
Yes.
Symmetrical
Yeah.
relations. Didn't you, at least in theory, solve the problem about RDFS not having the support by just having a relation about one by one way, one with the other?
Yes, that's it. That's it. But you can do that. Here, it is connected really to the yeah. You can describe a property of symmetric type, but it is not visible. So you will duplicate this description basically. But for some reasoners, you should be able, so depending on the property, kind of infer the other way around. So that's and this basically is solved by adding the a property to a property, so that this property is symmetric, and then the reasoner can kind of do this inference. Yeah, so now we back to some predicates, but yeah, but now I mean this formula or formal presentation is linked to what you can also do in OWL. So we have well, woman, which is person and female, and person and, well, in this case not woman, and etc. etc. So this kind of flexibility you have with OWL. And the so talking about inference, so that comes back to your question. So in many so this is what you can do is, in the simplest case with the ontologies is to infer not explicitly stated facts. So that will be a job of the logic motor that you have. So given certain description, it can also, for example, conclude that grandmother is a subclass of man and a woman and such. So while not explicitly stated. Okay, so well, I will not go through this example. So you can also run it through the converter and visualizer. And then again, so this and other slides is just to show that with OWL you have the flexibility to basically describe most of the needed semantical relationship between world objects, such as so here is multiple inheritance, so green round shaped 2D object. So it's a subclass of two different classes. So now we are kind of moving towards more from knowledge representation to more of kind of supporting certain type of reasoning. Can you just give me... My son is ringing me. So different flavors of partonymy. This is very important, actually. Oh, can you give me a second? I don't know what. Where I have been, yeah. Yeah, so I probably skipped the slide. I lost what I want to say. Here, again, some differences to the first version of all, maybe not very important, but again, so it's a support to do this, to add this find the details on which further contribute to semantical description. And in such a way, so what you can do, you can, I mean, as a simple example, so you can describe yourself as a I mean, you can create an ontological description of yourself. So linking to some to the descriptions from other ontologies and the other places, basically. So that we will see in next classes. This is something that maybe I don't know, frankly, again, so I maybe if I want to answer the question that you probably could state. I don't know how RDFA is actually useful or used in general, maybe not very much. But again, so the idea was to create a symbiosis of web and ontological description. And I think, so I just wanted to mention it because just to give you some feeling where it meant to go. So the idea was to really, when developing an information resource, like the web page, not only to write a text, but also to annotate it in such a way which can be understandable by machines. I mean, so it's semantically treated. So the idea is that, so if wait, yeah, so here is an example of a classical way of creating web pages where you just have a HTML document which is parsable by browsers, and to transition it to something which looks like this. So where you would annotate and or you would embed semantic information into your description. So in this very way. What you can do with this, and that's what I want to show. So again, so that was an idea. So let me see what's going on here in the chat in the meantime. Okay, so that was a lot. So you can go to this website over here. Now, let me see if I have it. Maybe I already. No. Yes, I know. Yeah, whatever. Yeah, so this is just a playground to try this RDFA concept. So let me just copy this annotated text. Control C. No. So to see how it would be parsed. I mean, by the browser, and actually by a machine that wants to extract certain information. So you see that this is the main deviation from just keyword-based search. So a web resource would become a piece of semantically loaded information. So what do you see here is, so I annotated that, so we have a property, a property name, so of a person, I guess, and maybe a person has a nickname again. But then I also, I mean, so this is a property related to my professional activity, including the affiliation. And later on, all this stuff can be linked to further ontological descriptions of this stuff. So that is it. So we have a web page, which is essentially describes a person with name, nickname, title, and affiliation, and such. I think it's kind of cool. Who knows how the technology would look like if it would be mainstream, or if it will be mainstream. Okay. Next. And finally, in the remaining minutes, I want to introduce a tool for working or for creating ontologies. That's what we will use in your lab too, which is called Protégé. Protégé, I guess. Yeah, to do that, we need to download a software, and I am trying to locate where there was a slide, I guess here. Yes. So this Protégé development environment exists here. I think I already. Yes, it's over here. So you can find lots of information on how to use it, and the documentation. Well, for me, it displays version for Mac. It exists for obviously for Windows. Right, and so if you do that, this is how it looks. Let me see. So I just want to let me start it over. Wait. Do you want to save? No. So Protégé. So this is the starting view, and you can start with developing your ontologies here from scratch, or you can. Yeah, and by the way, so later on, so we would need to load some reasoners, so that the motor, the reasoning motor. So I won't do that now. But what I did, or what I want to do is, so I want to go back to my website. So we can use basically some ready created ontologies. We just will be able to locate it. D0034 ontologies, and maybe I won't let it be cars. Yes. Well, actually, I mean, you can obviously look at these files and try to understand, but by no means they are ideally created ontologies. So rather, I adopted it from somewhere. So previously it was adopted from somewhere. I populated with my information, so it's a little bit kind of maybe not very consistent with respect to information presented in there. But what you can do, so you can take this address to this ontology, so you can and you can load it to Protege for kind of further inspection and modification. So you go from open from URL and do this. So, and here you go. Here you go. You can go to entities, and here you have this thing, and then you have different categories. So you, along with some instances. So I think I hope next time we will look at some details of it. But I mean, that's what you will be working with in lab 2, basically. No, I mean. So the main message here is that, well, RDF, RDFS, all, so it's a language, I mean, XML, kind of not very readable, as you see. But to our advantage, we have this tool with the graphical representation, with graphical development environment, which facilitates working with all these documents, which otherwise is very easy to make mistakes, obviously. Right, and so next week, so this would be my last slide. We will continue looking at ontologies and basically from the point of view what you can do with it. So if you have ontological descriptions, so what kind of so how can you query them? So we will look at Sparkle, semantic query language, which is used in this context. Yes, and that would be it for now. See you next week.